Today in DC electrical circuits, we're going to be looking at lab number 11, Thevenin's theorem. The objective of this exercise is to examine the use of Thevenin's theorem to create simpler versions of DC circuits as an aid to analysis. Multiple methods of experimentally obtaining Thevenin's resistance will be explored. Under reference sections, we'll be referring to Sham's Outlines, Basic Electricity, 2nd edition, and specifically we're going to be looking at Chapter 9, Network Calculations. We're going to be looking at Thevenin's theorem and series parallel circuits. So Chapter 9 is Network Calculations, and we're interested in Thevenin's theorem. And it says here, Thevenin's theorem is a method used to change a complex circuit into a simple equivalent circuit. So you can see here in figure 9-8, they start with complex circuits. They short out the power supply to find out what R Thevenin is, looking back into the circuit. And then they simplify the circuit using V Thevenin, which is the open circuit voltage without a load on it, and R Thevenin, which we just calculated looking back into the circuit without the power supply attached. And then in figure 9-9, they show you Thevenin's equivalent with a circuit load. So under Theory Overview, it says the Thevenin equivalent will produce the same load current and voltage as the original circuit to any load. So this makes your calculations a lot easier if you Thevenize the circuit before you put different loads on it. Okay, it says the Thevenin voltage is found by determining the open circuit output voltage. The Thevenin resistance is found by replacing any DC sources with their internal resistances, and for a voltage source that's 0. And then we determine the resulting combined resistance as seen from the 2 points using standard series parallel analysis techniques. So under equipment, I'm going to be using the Agilent DC power supply, model number E3630A. And the serial number is a little too hard to find, so I didn't bother with it. I just put an X through there. The digital multimeter is going to be the Mastech MSM 9803. Again, not bothering with the serial number. I've already gone ahead and measured the resistance of my resistors. So my 2.2K came out to 2.177K. My 3.3K came out to 3.255K. My 4.7K came out to 4.61K. And you'll notice the change in the number of decimal places because our digital multimeter is auto-ranging. So once it gets past 4, it has to move up 1 range. My 6.8K came in at 6.7K ohms. My 8.2K is 8.05K ohms. And my 10K potentiometer came in at 9.82K ohms. On page 2 of the lab, I've gone out on the internet and found some pictures of the resistors that we're going to be using today, and I've come along and also put down the colors associated with those values. So our 4.7K is going to be yellow, violet, red. So under procedure, step number 1, it says consider the circuit of figure 11.1. Using E equals 10 volts, R1 is 3.3K, R2 is 6.8K, and R3 is 4.7K. And our load resistor, which is R4, is equal to 8.2K. It says this circuit may be analyzed using standard series parallel techniques. We're to determine the voltage across the load, R4, and record it in table 11.1. And we're to repeat the process using 2.2K for R4. So looking at figure 11.1, what we want to do is determine the voltage across R4. So what we have is a 10 volt supply. R1 is 3.3K, R2 is 6.8K, R3 is 4.7K, and R4 is our load resistor, and it's 8.2K ohms. So in order to find the voltage drop across our load, I need to know what the voltage is at point Y. So in order to do that, I'm going to take the series total of R3 plus R4 and find out what the resultant resistance for the parallel series circuit is, so that I can use the voltage divider law to find out my voltage at point X, and then using voltage divider law again, I can find out what my voltage is at point Y. So looking at my calculations with the R4 load resistor at 8.2K ohm resistance, the resistance of the parallel series branches is equal to R2 in parallel with R3 plus R4. So that's going to be equal to 6.8K times 4.7K plus the 8.2K divided by 6.8K plus 4.7K plus 8.2K. And that works out to 4.453K ohms. Remember, this form of trying to figure out the parallel equivalent resistance is called the sum over the product. So using voltage divider law to find my voltage at point X, I take the resistance of the parallel series branch divided by the total resistance of the circuit, which is R1 plus the resistance of the parallel series branch, times the 10 volts that's applied to the circuit. So the calculation becomes 4.453K divided by 3.3K plus 4.453K times the 10 volts. And that works out to 5.744 volts. Now to find the voltage at point Y with respect to ground, which is also the voltage drop across the load resistor, which is also the voltage across R4. So that's going to be equal to R4 divided by R4 plus R3 times the voltage at point X. So that's equal to 8.2K divided by 8.2K plus 4.7K times the 5.774 volts, and that works out to 3.65 volts. So in table 11.1, under V load theory, for the 8.2K ohm load resistor, the voltage will be 3.65 volts. So now we're to repeat the process using 2.2K for R4. So the first step is to find the resistance of the parallel series branches. So this is going to be equal to 6.8K times 4.7K plus the 2.2K divided by 6.8K plus 4.7K plus the 2.2K, and that works out to 3.425K ohms. Now to find the voltage at point X, that's going to be equal to 3.425K divided by 3.3K plus the 3.425K times the 10 volts applied, and that works out to 5.093 volts. To find the voltage at point Y, which is the voltage drop across the load resistor, that is equal to 2.2K divided by 2.2K plus the 4.7K times Vx from above, which is 5.093 volts, and that works out to 1.62 volts. So in table 11.1, under V-load theory, for the 2.2K ohm load resistor, I record V-load as being 1.62 volts. So under procedure, step number 2, we're to build the circuit of figure 11.1 using the values specified in step 1, with our load, which is R4, is equal to 8.2K. We're to measure the load voltage and record it in table 11.1, and we're to repeat this with a 2.2K ohm load resistance. We're to determine and record the deviations, and it says do not deconstruct the circuit. So I just wanted to show you my circuit wired up. You can see I have 10 volts and I've pressed in the plus 20 volt button for the meter, so I am getting 10 volts. The common is the black terminal, and the plus 20 volt output, the red lead, that's going to supply my 10 volts. So I have 10 volts coming into my 3.3K ohm resistor that's making contact with my 4.7K ohm resistor. At the junction is R2, which is 6.8K ohms. On the other side of R3, which is the 4.7K ohm resistor, I have my load resistor, and this load resistor is 8.2K ohms. The bottom of the 8.2K ohm resistor is joined to the bottom of the 6.8K ohm resistor with this little black wire. On the other side, the black wire goes back to the common of the power supply. I have the red lead from my voltmeter placed on the top of my 8.2K ohm resistor, and I have the black lead of my voltmeter on the bottom of my 8.2K ohm resistor. My voltage reading is 3.658 volts. I've now replaced the 8.2K ohm resistor with the 2.2K ohm resistor. And my voltage reading is 1.636 volts. So in table 11.1, under V-load experimental, for the 8.2K ohm load resistor, I measured 3.658 volts. And under V-load experimental, for the 2.2K ohm load resistor, I measured 1.636 volts. I'm going to leave you to calculate the percent deviation. Under procedure, step number 3, we're to determine the theoretical Thevenin voltage of the circuit of figure 11.1 by finding the open circuit output voltage. This is replace the load with an open and calculate the voltage produced between the two open terminals. We're to record this voltage in table 11.2. So to find E Thevenin, what we're going to do is we're going to open the circuit. So we're going to remove R4. So now we want to know what the voltage is going to be with respect to ground, and that's going to be our E Thevenin with R4 open. So if you remove R4 from the circuit, current will flow through R1, through R2, back to the common. But because R3 is now open, no current will flow through R3. So the voltage for E Thevenin is going to be equal to the voltage at the point between R1 and R2. So it becomes simple voltage divider law where we take R2 over R1 plus R2 times the applied voltage will give us the voltage here, and because no current's flowing, there'll be no voltage drop through R3, so it'll be the same on our output with the load resistor removed. And this is E Thevenin. So doing the calculation, E Thevenin is equal to R2 over R1 plus R2 times the applied voltage. And that's equal to 6.8K divided by 3.3K plus 6.8K times 10 volts. And that equals 6.7 volts. And note that's with R4 open, no current flows through R3, so there is no voltage drop across R3. In table 11.2, under theory, for E Thevenin, I record 6.7 volts. Under procedure, step number 4, it says to calculate the theoretical Thevenin's resistance, first remove the load, and then replace the source with its internal resistance. For a voltage source, this is ideally a short. Finally, determine the combination series parallel resistance as seen from where the load used to be. We're to record this resistance in table 11.2. So now to find Thevenin's resistance, what we're going to do is remove the load, and we're going to look back into the circuit from the point of view of the load. Now we're going to replace our voltage source with a short. So we actually take the voltage source out of the circuit and replace it with a short. We never short out a power supply. So from the point of view of the load resistor looking back, we can see that there is a 4.7K ohm resistor, and it's got two resistors that are now in parallel due to the short, that now come and feed back to the bottom of our load resistor that's being removed. So R Thevenin is going to be equal to 4.7K plus the 3.3K in parallel with the 6.8K. So looking at the calculation for Thevenin's resistance, we can see that R Thevenin is going to be equal to R3 plus R1 in parallel with R2. So that's equal to the 4.7K plus the 3.3K times 6.8K divided by 3.3K plus 6.8K. And please note the parentheses or the brackets around this particular part of the equation is the R1 in parallel with R2 that needs to be calculated before you add the 4.7K. So this works out to 6.9K ohms. In table 11.2, under theory, for R Thevenin, I recorded 6.9K ohms. Under procedure, step number 5, it says the experimental Thevenin voltage may be determined by measuring the open circuit output voltage. Simply remove the load from the circuit of step 1 and then replace it with a voltmeter. Record this value in table 11.2. So in my circuit, I've removed the load resistor, and my voltage reading is 6.74 volts. So in table 11.2, under my experimental reading for E Thevenin, I've recorded 6.74 volts. Under procedure, step number 6, there are two methods to measure the experimental Thevenin's resistance. For the first method, using the circuit of step 1, replace the source with a short. Do not simply short out the power supply. Disconnect the power supply from the circuit, then replace it with the short. It then says, replace the load with the ohm meter, the Thevenin resistance may now be measured directly. We're to record this value in table 11.2. So what we're going to do is we're going to disconnect the red lead from the plus 20 volt terminal and put the red lead into the back of the black common banana lead. You notice there's no yellow lights on the power supply. We still have our circuit from the previous step, and you can see that there is no load resistor in here. So in our digital multimeter, we're going to rotate the dial from volts to ohms, and you can see our reading is 6.8k ohms. So in table 11.2, under experimental for our Thevenin, I've recorded 6.8k ohms. Under procedure, step number 7. It says in powered circuits, ohm meters are not effective. An alternative method relies on measuring the effect of the load resistance. We're to return the voltage source to the circuit, replacing the short from step number 6. For the load, insert the potentiometer. Adjust this device until the load voltage is half of the open circuit voltage measured in step 5. Remove the potentiometer from the circuit and using an ohm meter, measure its resistance and record it in table 11.2 under method 2. At this point, the load and the Thevenin's resistance form a series loop as seen in figure 11.2. So looking at figure 11.2, you can see that Thevenin's equivalent circuit is made up of E Thevenin, R Thevenin, and the load. So it becomes a simple series circuit. This means that they see the same current. If the load exhibits one half of the Thevenin's voltage, then the other half must be dropped across the Thevenin's resistance. That is, V of R load is equal to V over R Thevenin. So consequently, the resistances have the same voltage and current, and therefore must have the same resistance according to Ohm's law. So you can see I've replaced the load resistor with a 10k ohm potentiometer. The center pin of the 10k ohm potentiometer goes to common and the black lead of the voltmeter. The top pin of the potentiometer goes through this green line to my 4.7k ohm resistor. Now E Thevenin was 6.74 volts, so I've adjusted my potentiometer until the voltage reading is close to 3.37 volts. So this is the reading on my voltmeter, 3.371 volts. To measure the resistance from the top pin to the center pin of my potentiometer, I have to disconnect it from the circuit. Rather than pulling it out of the circuit and trying to measure across those two pins, what I'm going to do is disconnect the 4.7k ohm resistor from the circuit. Now I'm measuring between the center pin and the top pin of my potentiometer with a break in the circuit. So turning the dial on my digital multimeter to ohms, you can see I'm reading 6.78k ohms. So in table 11.2, under experimental for R Thevenin, method number 2, I've recorded 6.78k ohms. Under procedure, step number 8, it says consider the Thevenin equivalent of figure 11.2 using the theoretical E Thevenin and R Thevenin from table 11.2 along with 8.2k ohm for the load. We're to calculate the voltage and record it in table 11.3 and repeat the process for the 2.2k ohm load resistor. So in figure 11.2 we have Thevenin's equivalent circuit, and we calculated E Thevenin to be 6.7 volts, R Thevenin to be 6.9k ohms. So now we're going to use Thevenin's equivalent circuit to calculate the voltage drop across the load. So in the first instance, R4, or the load resistor, is 8.2k ohms. So the calculation is simple voltage divider, where VL equals RL over RL plus R Thevenin times E Thevenin. So in this case, it's 8.2k divided by 8.2k plus 6.9k times 6.7 volts. And that works out to be equal to 3.64 volts. In the second case, we're to do the calculations for the R4 load resistor equal to 2.2k. Using the above formula, we can see that VL is equal to 2.2k divided by 2.2k plus 6.9k times 6.7 volts, and that equals 1.62 volts. So in table 11.3, under V-load theory, for R4, the load resistor at 8.2k, I've recorded 3.64 volts. And for the 2.2k ohm load resistor, I've recorded V-load theory as 1.62 volts. You'll notice these numbers are very close to what you recorded for V-load theory in table 11.1. Under procedure, step number 9, we're to build the circuit of figure 11.2 using the measured E Thevenin and R Thevenin from table 11.2 along with 8.2k for the load resistance. We're to measure the load voltage and record it in table 11.3. We're also to determine and record the deviation. So from table 11.2, we're going to set our power supply to our experimental E Thevenin of 6.74 volts. And we're going to adjust our potentiometer to get as close to the experimental value of R Thevenin of 6.8k ohms. So I've adjusted my potentiometer till it says 6.9k ohms. So on my power supply, I'm using the plus 20 volt terminal and the common terminal. And on the plus 20 volt meter, you can see I'm reading 6.71 volts. So trying to get you a really good view of my circuit is not easy, but the 6.7 volts comes in and goes to the first leg of my potentiometer. The center leg, which is the wiper, goes to my 8.2k ohm resistor. And the 8.2k ohm resistor goes back to common. So I have the red lead from my voltmeter coming in and going to the top of my 8.2k ohm resistor. And I have the black lead from the voltmeter coming to the other side of my 8.2k ohm resistor. So I'm reading the voltage drop across the 8.2k ohm resistor. And you can see my voltmeter is reading 3.62 volts. So in table 11.3, I've recorded 3.62 volts. Under procedure, step number 10, we're to repeat step 9 using a 2.2k ohm load resistor. So I've replaced the 8.2k ohm resistor with the 2.2k ohm resistor. The red lead from the voltmeter goes to the top of the resistor. The black lead from the voltmeter goes to the bottom of the 2.2k ohm resistor. So I'm reading the voltage drop across the 2.2k ohm resistor. And the voltmeter is reading 1.613 volts. So in table 11.3, for V-load experimental with a 2.2k ohm load resistor, I've recorded 1.613 volts. As usual, I'm going to leave you to calculate the percent deviations. On the last page of the lab, there are 3 questions for you to answer based on your calculations, results, and observations you made during the lab. When you've completed your lab, leave your circuit set up on your trainer so you can show it to your instructor so that they can verify that it is working, and then they will initial your lab to indicate that it is complete.